So we have this very important equation here, Q is equal to CV. And as we said before, then C is equal to Q divided by V, C in coulomb, V in volt, and therefore that has a unit of farad. Now, next we're going to look at how we're going to charge up a capacitor. A capacitor is represented, the positive plate is straight and the negative plate is curled in some representation. And we have a voltage of V across the plates, and we are going to charge the plates with a current of I. Now, as we said before, we have the very basic equation, which is Q is equal to C times V. And these are functions of time for both the charge deposited on the plate as well as the voltage that is across the plate. So if you differentiate that, dq dt with respect to time is equal to C dV dt. And we know that this is current because the amount of charge deposited on plate, as you change that charge over time, that is the current that flows into the capacitor. So we have basically, let me just write down again, that the current into a capacitor is changing the voltage V of t that satisfies the differential equation, which is I of t equals C dV dt. This is called the integral, the differential form of the equation. And if you look at the capacitor voltage, what you have here is then V of t will be given by I of x dx, and then you have to integrate that from 0 to t, and you will have that, if you account for the initial value at time t0, you have a voltage of t0 plus 1 over c of I of x dx integrated from t0 to t. So that is the so-called integral form of the voltage current relationship across a capacitor. Now, we are going to look at energy store. As we pointed out earlier, that W, the work or the energy that's stored in the capacitor, is equal to 1/2 of C V squared of T. So we're going to derive how this particular equation. So what we have here is that we know before that power as a function of time is equal to I, the current, times V at the time t. So what you have here is that this is basically, if you integrate this from 0 to t of p of x dx, you're integrating over time the power that is injected in the capacitor. At the end of time t, you will have the total amount of energy stored inside the capacitor, which is Wc of t. Now that is equal to the integration from 0 to t of I of x V of x dx, which is from this equation here. So what you have here is that if you look at from 0 to t, and given the fact we have I of t is equal to C dV dt, and we can write that I of x would then be equal to C dV x dx times V of x dx. So if you kind of cancel out the dx here, what you have is from 0 to t of C of V of x dV of x. And this integration by parts give you 1/2 of C V of t, the whole thing squared. So we have proved this equation here, which is the amount of work that is stored inside capacitor is 1/2 of C times the voltage squared. Now, we're going to look at a few examples of charging a capacitor. For example, let's look at this charging current into the capacitor. What you have here is that you have a charging current that is a constant of 1 ampere from time 0 to time 1 second, and then it will be a negative current of 1 ampere from time 1 second to 2 seconds. So the question is, what is the voltage across the capacitor? Which equation are we going to use here? Now we are given the current I sub t. In order to find the V sub t, we have to do the integration. So if you look at this curve here, we need to integrate this over time. So what you have here is that as the current flows into the capacitor, the voltage keeps increasing. It starts from a voltage of 0. Initially, the capacitor is not charged, and then it will keep increasing until all the charge that is inside this area, basically 1 ampere times 1 second equal to 1 coulomb. In 1 second, 1 coulomb will be deposited into the capacitor. And since the capacitor has a capacitance of 0.2 farad, that 1 coulomb will raise the voltage to 5 volts. So what we're going to see here is this voltage increase from 0 to 1 second, increasing from 0 volt to 5 volt, which is 1 coulomb divided by 0.2 farad, and therefore is equal to 5 volt. After 1 second, the current becomes negative and is pulling charge out of the capacitor. It reverses direction, and therefore from 1 second to 2 seconds, the voltage dropped from 5 volt back to 0 volt. If you look at the work that is done imparted into the capacitor, we will have to use this equation, which is 1/2 CV squared, and therefore increases from 0 quadratically to 2.5 joule. At the end, you have 5 volt, 0.2, you have 5 volt here, and you have a 0.2 farad. You plug in the number, 1/2 of CV squared would be equal to 2.5 joule. So if you look at the curve here, it increases from 0 to a maximum of 2.5 joule in a quadratic manner, and then after that it decreases again to 0 after 2 seconds.